So our first speaker in the session is Peter Tropper, who's going to be talking about some experimental piston cylinder work. Take it away in your own time. Thanks.
A little bit of an experimental component to the research in metamorphic rocks. I'm going to be talking about the experimental simulation of geodynamic processes using a piston cylinder loop experiment. And I'm going to be looking at the subduction PT pass of a natural metapelite sample. Well, because of the temperature dependence of diffusion processes, only small parts of metamorphic PT pass are recorded in the rocks. And the question that arises is, what is the mineralogical memory of a rock, and how much information of a PT pass is actually retained in the rock? So when one tries to put experimental constraints on high-grade metamorphism of natural samples, one normally does a single PT stage experiment in the piston cylinder, for instance, here at 700 degree and 0.8 GPa. But what happens if we do multiple PT stage experiments, sort of a PT loop? And this is what we've been doing here. We've been running these PT conditions subsequently, so without taking the sample out of the machine. And the aim of this investigation is to simulate a PT pass of subduction zone metamorphism and look at the mineralogical memory of the sample. When we look at subduction zone PT pass, as you've seen here in this compilation, we know that P and T max coincide, and we do mostly have an isothermal cooling pass. So in our case, we tried to model this with a three-stage experiment. Stage 1 was at 500 degree and 1 GPa. Stage 2 was at 600 degrees and 1.8 GPa. And stage 3 was at 500 degrees C and 0.5 GPa. And each of these stages was run for 8 days. And before we then move on to the next stage, so the total duration of the experiment was 24 days. The starting material was a powdered sample of an amphibolite facies metapelite. It's a metapelite typically with chloride, garnet, muscovite, quartz, albite, and rutile. With respect to the chemical composition, it does have some sodium and potassium. So it's basically a very muscovite-rich rock. And garnet is only there, as there's very, very little garnet in this sample. Well, so after we ran the experiment, we took the charge out of the machine and looked at it in the backscatter electron images. On the left side, you see a bit of an overview. You see that there are reaction domains that occur here, interspersed between quartz and muscovite. So those are newly grown amphibole aggregates. And if one looks a little closer, you can see that these amphibores, they usually form in the former plagioclase domains. Chloride has gone from the sample. Here are two microdomains. There's a garnet microdomain. You see this garnet did not react, but it sort of broke down. You see all these resorption rims here. Garnet and plagioclase reacted to form amphiboles and quartz. And rutile is replaced by ilmenite in the experiments. When we look at the amphibole domains, if you look very careful, there is we can distinguish three different amphiboles. Amphibole 1 is a calcium sodium amphibole, which is a bit more calcium rich than amphibole 2, which is also a calcium sodium amphibole. And then we do have tiny specks of amphibole 3, which is actually an iron magnesium amphibole. If we look into this domain, we do see two kinds of amphiboles. We have this amphibole 2, which is a sodium calcium amphibole, and in the fractures here and then on the rims of amphibole 2 grows the iron magnesium amphibole 3. Yeah, when we look at the petrographic overview, as I said, the starting mineral assemblage was garnet, muscovite, chloride, albite, quartz, and the newly formed mineral assemblage is amphibole with three different amphibores, another generation of muscovite, ilmenite, and quartz. How can we interpret these amphibore forming reaction textures? Well, it's most likely a reaction where garnet and plagioclase react. Then we form glaucophane and paragonite in quartz. This paragonite occurs as paragonite component in the second generation of muscovite, or it could be garnet, plagioclase, and chloride reacting to form these sodic amphibores. Amphibore 3, the iron magnesium amphibore, can form prograde theoretically by a reaction between garnet and plagioclase, but it can also form retrograde by a reaction between glaucophane and quartz. And the textures, as we see here, they indicate that this coming tonight, this iron magnesium amphibore, probably most likely formed during stage 3 during retrogression. The mineral chemistry of these amphibores shows they're mostly sodium calcium amphibores, which we can classify as winchites and baroicides. When we look at the chemical zoning in the amphibores, one can see very rarely we do have a bit of a zoning pattern. The cores of these amphibores, these newly formed, they are slightly more calcium rich than the rims. So, for instance, the amphibore 1 is the one that contains a little bit more calcium. Amphibore 2 contains much less calcium. And the most important substitution in these amphibores is the glaucophane vector. So we do have an evolution of amphibore composition as a function of pressure. Again, with the muscovites, we do have two generations of muscovites. The newly formed muscovites, muscovite 2, they are silica rich, and they contain also a higher paragonite component, which is according with the interpretation that paragonite and glaucophane, for instance, are forming by the breakdown of garnet and plagioclase. I've done some pseudo-section modeling using the Teriac Domino software by De Capitani and Petrakakis. I won't go into the details here. We do have a lot of phase fields. We did not make a garnet correction to the bulk composition because the modal abundance of garnet was way below 1%. But it turns out that the comparison between the observed and the calculated mineral assemblages is rather poor. In the experiment, we do have a reduced mineral assemblage, ilmenite, muscovite, quartz, and amphiboles. The calculations predict a lot more phases. For instance, biotite, epidote, or garnet, and even amphosite, which we do not find in the experiments. I've also compared these results to a study by Proya from 2003, which deals with the formation and exhumation of glaucophane-bearing rocks. The agreement is again okay. We do find muscovite and the amphibores. He got garnet in his calculated assemblage, but it'd be interesting if my rock composition would actually follow this path. So if you could model this, for instance, a bit longer, then we should end up with a mineral assemblage that does not contain any high-grade minerals such as glaucophane. They should all be reverted to paragonite and biotite. Well, the resume of these experiments is that these experiments show that the forward modeling using whole rock PT loop experiments yields textures and mineral compositions that are comparable to natural metamorphic rocks. We can do this with different geodynamic settings. I've run collisional orogeny paths. We've run the subduction zone paths. So the textures are really comparable to natural rocks. We can see a textural sequence of mineral growth. We do have these amphibores, these three different. They reflect certainly changes in PT conditions. And when we combine the textural, the textural and the chemical data, then we can attribute these amphibores to stages 1, 2, and most likely 3. The thermodynamic model, on the other hand, still, of course, needs improvement. Well, the resume of this talk is basically if you combine field and petrographic data with experimental observations and thermodynamic modeling, then you will be able to really comprehensively characterize the metamorphic evolution of a given rock. So this is my message, that when you do experiments on the metamorphic evolution of a rock, just don't do only one PT stage, try to model different PT stages, because then you might actually end up with an equilibrium mineral assemblage. With that, I'd like to thank you for your attention.
Okay, thank you very much. We've got plenty of time for some questions. So the first one from Mauricio is, how many phases were selected for the actual modeling side of the study?
Well, I didn't select any phases. I used a natural rock, which contains 5 or 6 different phases. So I was just powdering up a rock, so I did not select minerals and mix them together. So I just used a natural rock.
So the I'm not sure if that answers the question. We'll move on to the next one. Maybe he'll ask a bit more detail. So the next question is, what about the kinetics in your experiments?
Kinetics is certainly a problem. We've done when we ran the collisional PT pass of a sample. I did also single PT experiments to compare the results to the PT loop experiments, and it turns out that, for instance, in the single PT experiments, you never make staurolite, you make chloritoid, and in the PT loop experiment, you make staurolite. So there seems to be some metastable equilibria, because the staurolites also contain hercinite inclusions. So kinetics does play a role. And maybe the run durations also need to be changed to much longer.
Yeah, okay. So yeah, I mean, that was going to be my question, but I'll save that if we have time. So another question about fluids. Do you have any fluids in the starting composition? And if so, what was its composition?
Yes, I added about 10%, and in another experiments, 20% of water, just as a flux, as a catalyst.
Okay. Inesh points out that it's interesting that you stabilized ilmenite and that rutile was not stable at high pressures.
Well, that actually agrees with the thermodynamic calculations, surprisingly.
Yeah, so I mean, with the experiments, can you lengthen the time at all? Is there a limit?
Yes. No, they can be run for a very long time. So might it be interesting to run them, for instance, every stage for about 3 or 4 weeks. Yeah. So then you definitely get a better recrystallization, and maybe even better. Yeah, how should I say? Maybe you see the chemical zoning even better.
Sure. And have you compared not running the retrogression stage, so just running the first part of the PT loop and taking out?
No, I haven't done this with this experiment. With the collisional PT pass experiment, I've done that, and it barely shows any changes. I mean, these 500 degrees and 5 kilobars, there isn't much going on. I was surprised. I was hoping for a bit more chloride formation, which should form from the amphibores, but it didn't happen.
Okay. So we got, so Mauricio just wanted to confirm that about the number of phases. He was talking about the pseudo-section modeling rather than in the experiments.
In the pseudo-section model. Well, in the pseudo-section modeling, I've ran the bulk composition, and the number of phases that occurred was about 6, I think 6.
Okay. So I think we just got one final quick question about have you varied the amount of water during the experiments at all?
Not in this other experiment I did, and it turns out that the resulting mineral assemblage is much more coarse-grained. So water helps.
Okay, thank you very much.